Alright, so where were we? We are studying context-free grammar. We have seen that context-free grammars are made of many rules. Each rule looks like this: a variable that can be expanded into a string. This string can have length, anything from length 0 to length not infinite. It can be anything from 0 to a very high finite number. Alright, and the elements of this string can be either terminals. We have also learned what terminals are, and we have also learned what variables are. Right, and there is a special variable which we call the start symbol. So these were all the topics of our last video. Alright, so this is what we call a production rule. There can be one or more rules in a context-free grammar, and using those rules we can generate any string of the language of that grammar. So let's formalize our grammar a bit. So each grammar needs 4 things to properly define itself, just like we needed, I think, 5 things to properly define a finite automata. We need the set of variables. What are the variables that we have in that grammar? We need the set of terminals. We need the set of rules. This is the most important part. This is equivalent to, I guess, if you want to compare it with finite automata, I think this is the closest thing to a transition function. The transition function specified the rules of how the states are going to behave. These production rules define how the variables are going to expand it. Something similar, not the same. Anyway, we also need to know which of these variables is our start variable. So if you give me these 4 things, I can define the grammar. Alright, so let's define a few grammars, and not just any grammars. We already knew at the very beginning of the course, we already talked about that context-free language is actually a superset of regular languages. So if we have regular languages here, context-free languages actually encompasses it. So CFL, so every language that is a regular language is also a context-free language. So our definition of regular language was based on 4 operations: the OR operation, the concat operation. So yeah, I should write OR. Concat operation, we had the closure. Actually 3 operations, not 4, because I think, yeah, no, spelling is all right. Okay, so the 2 closures are basically the same, and we have a bracket which is not important, which means all of these operations can be constructed using a grammar, because context-free language also contains each and every regular language, right? So let's say we want to, let's first start simple. We want to create the grammar of this operation. So take a very simple example. Let's say our regular expression that uses this is A or B, right? So I need a grammar that can generate any string which this expression can generate. And looking at this expression can generate only 2 strings, A or B, right? So let me write a grammar. We need the start symbol. So this is our start symbol. This is a must. I can write it anyway, but I'm going to make it simple. S can be converted into, let's say, A. S can be also converted into B. A can be converted into the terminal A, and B can be converted into the terminal B. Looks good, right? And using this grammar, you can, this is basically S can either be this A, and or S can be B, and in turn A can produce the terminal A or the terminal B. I could have actually written this more shortly. I didn't need to use the variables A and B because they are redundant, I can just write SP. Okay, so one more thing, when we have two production rules in a grammar which have the same left hand side, we don't need to write it separately. We can just write it like this. So S can be converted into A or S can be converted into B. So this grammar, by the way, this is actually two production rules. This is not a single production rule. I have written two production rules, SA and SB, together in this one line. So they are just two production rules. Anyway, so these two rules can simulate the OR operation. Similarly, if we have concatenation AB, I can just write S can be converted into AB, and there is that. The star is a little more interesting. So let's say we have A star, which means I can generate any number of A. So the grammar for this is going to be S can generate A, but not only one A. So I'm going to keep the S here. So see what's happening. Every time I'm using this symbol, I'm generating one more A, but my S is staying the same. So I can use this production rule repeatedly and generate as many A's as I want. The only thing that is left is I need to terminate this generation in some way, because if I keep only this rule, see what happens. I'm using S to AS, and then I'm using this S to create one more S and one more if I want, but the S is staying there. I'm never going to finish the string like this. So I need a terminal rule, and that is why I can just use this, right? So this means S generates nothing, a string of 0, an empty string, which means at any time when I have decided that, okay, that's enough number of A's, let's say I want to generate 4 A's, so I'm going to use this one more time, A, and if I use this rule one more time, I'm going to this, and then I'm going to use this rule to terminate the string, A, and this is going to be converted into epsilon, which is just nothing. So there you see, star can be something star can be generated using this grammar. So I have got the grammar for OR, the grammar for concatenation, the grammar for closures, which means anything that you can create using a regular expression can also be created using a context-free grammar. All right, so let's see one more better example. All right, so let's say I want to create all the strings that look like this: 0 to the power n and 1 to the power, let's say we have already covered n, let's say 2n. This is going to be very similar to 0 to the power n, 1 to the power n. Let's just see that, recap. We saw that in the last example, but let's see that again. We are going to generate as many zeros, as many ones. So for each 0 there will be a 1, but I want to do it repeatedly, so I'm keeping the S intact, and let's say n can be anything greater or equals 0. So at any point, if I wish to terminate the generation, I need to convert S into nothing, which means the empty string. So this is the grammar for the language where each string looks like this. Now, when I put 2n, the only difference you have to make in this grammar is that for each 0, this rule is going to be 0, S, 1, 1. That's it. For each 0, you're going to generate 2, 1. All right. So this is the grammar for all the strings that looks like this: 0n, 1, 2, 2n. Not very hard, right? All right. And how about some more example? Okay, so this is a good one, the grammar for all valid mathematical expressions. So what are valid mathematical expressions? I can say that 3 plus 4 minus 5 is a valid mathematical expression. I can say 5 into 5 divided by 2 is a valid mathematical expression. Now, what is not a valid mathematical expression? I guess you can say this is not a valid mathematical expression, right? This makes no sense. So we can actually write a grammar for all possible valid mathematical expressions very easily. Let's say, so the base case here is that each number is a valid mathematical expression, right? 3 makes sense. 3 means 3. That's it. 4 means 4. So each number is a valid mathematical expression. So if we have a variable, let's define a variable e, which is going to stand for expression. An expression can be a number. So here num is a terminal. Num can be any number which is a terminal. All right. So let's say, I'm not going to the details of how to generate numbers. Let's just say a number is a terminal. So e can be converted into any number. And for example, 34. 34 is a terminal, right? You cannot create more variables from 3 or 4. They are just literal symbols. Anyway, moving on. So if a number is an expression, we can always add 2 expressions, right? If I have a valid mathematical expression and another valid mathematical expression, if I add them or minus them or multiply them or divide them, all of these are valid mathematical expressions, right? So I'm going to get e plus e is also an expression. I will have expression minus expression is also an expression. Similarly, I'm going to have e into e and e divided by e, right? So we need more. Well, we need bracket, right? So if 3 into 4 is a mathematical expression, that is also a mathematical expression. So if e is an expression, this has to be another expression. So let's add that. And I think that's enough. I don't think we need anything more. And as we can see, we have only one variable in this entire grammar. So our start variable is going to be e. So let's see how it works. Let's see, I want to write the expression 4 into 3 minus 2 divided by into 4. All right, so I want to generate this expression. So let's start from our start variable. What do we have? We have, let's consider this as an expression first. So we have one expression into another expression. So let's use this rule. Let me use different. So we have e into e, and I'm going to break this one. As you can see, this expression is actually some expression minus another expression. So I'm going to use this one here, and this becomes e minus e. This stays the same. This expression is actually this one, which is actually some expression into some expression. Sorry, this is actually bracket. So I'm going to use this rule. So this e becomes bracketed e. I have, and I think you get the picture. If I expand this into using this again, so I have e into e minus e into e, and I can use this rule for each of these e to convert all of them into a terminal number. So the first one is going to be converted into a number. This one is going to be converted into a number. This is going to be a number into another number. And this number will generate, this number is going to be different numbers. I avoided that part. So let's just say that works. And I'm going to have different numbers for each of these. So I have got 4 into 3 minus 2 into 4. This actually needs more work, but to keep things simple, I'm just assume that numbers can be generated. All right. So you see, this works, and this is going to work for any valid mathematical expression you can write. All right, so I think that's enough example for a video, and we are going to have one more video for this class. In that video, I'm going to show you a couple of more definitions. All right, so up until then, goodbye.